All right, so number two, I'm going to follow the same steps I do with everything. First, I look at the diagram, just maybe because I'm visual, but I think it gives you a rough idea of what you're looking at. It looks like we have a circuit that's going down into some water with a stirrer in the bottom and a variable resistor over here. I'm not spending a ton of time looking at it, but I am looking at it to get a brief idea. And then I'm looking at the questions, determine the current, determine the power, explain why the water heats up, assume the stir has a knob and it changes its temperature. How can the temperature of the water be increased more rapidly by adjusting the rotation of the stir? And as the temperature of the water increases, explain the microscopic interactions for the changing pressure in the container. And again, I looked at the diagram and read the questions in under a minute and a half, if that. And now I know what I'm paying attention to when I'm reading the question. So the figure below shows an electric circuit containing a source of EMF E, variable resistor R, resistor of fixed resistance R. Again, things that we already knew from looking at the diagram, which means I don't have to process it because my brain has already processed it from the image. The resistor R is immersed in a sealed beaker containing a mass M of water at current temperature T sub I, the initial temperature. When the switch is closed, the current runs through the circuit, causing the resistor in the water to dissipate heat, which is absorbed by the water. So I'm just going to draw a little bit of radiating heat from the resistor to water so I remember that that's going on. You don't have to do that. Things that I'm going to do when I'm doing this question. A stir at the bottom just ensures that the temperature of the water is uniform throughout the water at any given moment. That's good. I was wondering why there was a stir down here. The apparatus is well insulated, which means it's not going to give off heat to the environment. And it may be assumed that no heat is lost due to the walls or the lid of the beaker or to the stir. Great. No heat, all of the temperature is contained within this container. All right, so we need to determine the current in the circuit once the switch is closed, and I'm gonna again underline my verb determine. That's what I need to do. Determine. That just means calculate, find out, find the answer. They don't want you to justify it. You might have to do some calculations to do it, but we're just determining current. And our answer needs to be in terms of these, so I'm going to circle that. And if you have more space between A and B, at the bottom of A, right above B, I'm going to write those variables that I have to work with so that when I do get at a final answer, I remember, oh yeah, it has to be in terms of those. And I know I'm spending a lot of time on this question, but hopefully these are your thought process when you're going through and solving the problem. All right, so knowing all of that, how are we going to approach this?
Well, we know, are we assuming an ideal battery? Because it doesn't state otherwise.
If it doesn't state otherwise, it's a fair assumption, I think.
Okay, then so we know the E or whatever that symbol is going to be substitute for the voltage. We're probably going to use the IVR equation.
Yeah, V equals IR. In which case, voltage is EMF, and we're still not at the final answer because, and I'm going to go ahead and say resistance total, right? That's the total resistance. Because the total voltage is equal to the current in series times the total resistance. So this is not big R, this is total R. So then where are we going from there?
So we're trying to determine the current. We know that. Okay, so we know the current is going to be equal to. Current equals the EMF divided by the total resistance, and total resistance is R plus big R.
Yep. And right there, we've done A. Beautiful. All right, now B, power. And again, I'm underlining the verb determine, and I'm circling what variables I need to determine it in. So how are we going to do that?
So power equals the current times the resistance?
Close. Your equation is off. It should be I times the voltage. But one other thing we need to pay attention to is they said not the power for the entire circuit, but the power dissipated by resistor R. So in that case, I'm going to replace my voltage with IR. So then our equation for power, IV, remember Barry Bonds gets his power from an IV because he injects. So then your total equation for power would be IIR, or I squared R. And because we already have current in terms of this, EMF over R plus R, well, it's going to be EMF over R plus R, and that whole thing gets squared times big R. And that's the power dissipated by resistor R. And it is in terms of the variables they've provided us with. Do you guys have questions up to this point? All right, C. At the explain. Again, I'm underlining my verbs. Explain at the microscopic level why water heats up when the switch is closed and how the stir helps ensure a constant temperature throughout. So I'm also paying attention to that word and, because that means I need to explain both things. And I say that because when I did this practice thing, when I did it myself, I only did the first half. I skipped the second half until I looked at the key and realized I didn't explain the second half. So always be careful. A reminder that this test is described as a reading test as much as it is a physics test. So explain at the microscopic level why the water heats up when the switch is closed. Who wants that? Who wants it?
I'll do it. Okay, so microscopic level, why the water heats up, switch is closed. Okay, so what it is the resistor is going to be dissipating some of that power that goes through it as heat in either vibrations or infrared light, or anything. It could be visible light if it wanted to, but we're just going to go with vibrations.
How is the heat generated in the first place?
I'm assuming it's just the electrons trying to push through and the resistor is resisting them.
Friction. Yeah.
What's not friction?
It's friction. It's
friction.
Where the electrons rub past bounce off of each other, and essentially the atoms rub against each other as a result.
Okay, all right. That makes sense. Okay. Also, I'm probably going to have to go after this question. I know I don't want to leave you alone, but I need to get a shower because we have school tonight. So
I understand.
Yeah, sorry.
No, you're good, man. Okay, so I'm good on the first half. We've explained why the water heats up when the switch is closed. And how does the stirrer help ensure a constant temperature throughout?
I can do that one too.
Okay.
Constant temperature throughout. So essentially what it's going to be doing is, as it moves, it's going to wick away some of those water molecules surrounding the resistor and replace them with fresh, cooler ones. And because the rate, this is asking ensure a constant temperature. So yeah, it's just going to move the atoms around and mix them up and make sure no one area gets too hot.
Perfect. All right.
So would a valid explanation be that the fan creates a convection current which distributes the heat?
Yep.
Okay.
I don't know. I think convection is no. I would say no, because convection is the result of heat being produced and rising up because the hotter molecules are less dense, as we discussed in the first question. So I would say no.
Okay.
Convection current is not describing the shape, it's discussing the process of hot versus cold and how it creates that circular loop. Hot rises, cools down, and then settles back to the bottom.
Although you could argue the stirrer is creating lower pressure because the water's moving faster towards the bottom, couldn't you?
You could make that argument. I would be okay with that, but they specifically wanted to discuss. Yeah, you could make that argument. Absolutely. I have no problems with that. Okay. D. Assume the stirrer has a knob which changes its speed. How can the temperature of the water be increased more? By adjusting the rotation of the stirrer. So how can it do that? They didn't give us a verb, but they're asking us how, so we need to explain how can the temperature of the water be increased more? By rapidly by adjusting the rotation rate of the stirrer. Go ahead.
Olin, do you want this one? I can do it, but...
Go ahead, I'm blanking.
Alright, so as the stirrer moves around, what it's going to do is replace hot molecules with cold ones, or cooler ones at least. And because we know that... I'm going to write an equation here, so if you want to get that ready. Delta Q over T is going to be equal to, I believe it's delta temperature times K times area divided by length.
KBT over L. That sounds right. I'm going to pull it up just in case.
KA? Not B-A.
KAT. KBAT, isn't it the Boltzmann constant, K sub B?
Oh, yeah.
Yeah.
Yeah, but you have to multiply.
I missed area. You're right.
And so a larger delta temperature is going to get a larger rate of heat transfer.
Does that work for this?
Yep. Kind of, I think.
You're saying the faster it spins, the greater the heat transfer?
Because heat should be the transfer of heat into or out of the container. So I don't think there is...
From the water molecule, okay, from the resistor to a water molecule. So...
Yeah, but that's not what they're talking about. They're talking about how can the temperature be increased just by increasing the speed of the stir.
Yeah. You increase the speed of the stir, that replaces the hot molecules nearby the resistor with cold ones, which is going to increase the delta temperature between the resistor and the water, which is going to increase the rate of heat.
Okay, so if you have a larger difference in temperature, you would be able to transfer heat faster. Wow, I did not approach it that way, but yeah, I agree with you. Good call. Yeah, that's 100% viable. I agree. An alternate viable explanation, the one I went with, is just you're adding more kinetic energy. You're taking power from whatever's powering this stir, and you're transferring it into kinetic energy of the water molecules. So because they're moving faster, you've added energy into the system, which is going to turn from kinetic energy into heat of the water, or increased temperature of the water, not heat. All right, and E, as the temperature of the water increases, whether from the resistor or from the stirrer, explain the microscopic interactions responsible for the changing pressure. So now, what happens to the pressure as a result from this increased temperature?
Okay, so I'm going to explain this in the most basic terms. basically air molecules heat up, they bounce around more, so they're going to be imparting more kinetic energy on the container, basically increasing the pressure.
I think that's perfect. Drew, do you have anything to add?
Not really. My explanation used momentum, but it works.
Perfect.